Okay, I am skipping. Okay, let's record. Okay, recording. I'm skipping number 3. I'm going to go on to number 4 in the interest of time. Unfortunately, I just don't have time to handle everything. So, 4 is the one. This is a true story, yes, about me. Not really about me, but it's about something I saw on the grounds of the Notre Dame Cathedral a couple of years ago when my lovely wife uh, got us some good plane tickets there over New Year's Eve. So it's about this sort of kids merry-go-round I saw on the cathedral grounds, and instead of that's a theta there. Instead of the axis of the merry-go-round and the platform being sort of horizontal and vertical like normal, they were tilted. So the axis around which the merry-go-round rotated was tilted along with the merry-go-round itself. So the platform still sort of spun in a plane, so to speak, but the plane it was spinning in was not a horizontal plane. And this is obviously the least perfect ellipse ever drawn, but there it is. You're going around at some angular velocity omega, and the radius of the merry-go-round is r. And I believe I gave values for all these in the problem, but unfortunately I can't find my copy of the problem right now, so I'm just going to have to go from memory. So the idea is this kid is sitting on the merry-go-round, and we'll represent the kid as usual with like a block or something. And the block has a coefficient of static friction of mu s with the merry-go-round surface. So spinning around here, the question is how fast, what's the maximum omega we can reach without the kid falling off? So, you think about this, there are really two possible places he can fall off, where you're going to have sort of the extreme cases for acceleration. You're going to have the top here and the bottom. So either he'll spin off when he's at the top up here or when he's at the bottom down here. So I'm going to draw a sort of a little sketch of what things look like when he is at the bottom. That is B-O-T-T-O-M is how we spell bottom. So, here's the mass of the kid, of course. So what are the forces acting on the kid when he's down here? Well, he's got, obviously, he's got his gravity or his weight like that. We've got a normal force from the merry-go-round. And finally, so he's not touching a cord, so there's no tension. He's not touching anything but the merry-go-round surface, so there's only this normal force and the weight of him. Pretty obviously, I'm going to go blue here for a second. This is when he's at the bottom of the merry-go-round, down here. So when he's down here, he has to be accelerating like that, okay? When he's up here, he has to be accelerating like that, okay? So down here at the bottom, he's accelerating that way, which means pretty obviously, if this is going to work at all, friction has to be pulling him upward. So there is the static friction force. So now I'm going to do this, do a free body diagram. FBD of the kid at the bottom. At bot, that's supposed to say. Trust me. Okay, so here is the kid's dot. We have gravity going down. We have a friction force going upward, static friction force, and of course we have a normal force going that way. Now, what is the angle involved here? Well, this angle here is going to be theta, okay? Because remember, the axis he's spinning around in this picture is tilted at an angle theta from vertical, so then the platform is also tilted at an angle from horizontal because the platform stays perpendicular to its axis. Okay, so this angle here is theta, and this angle here is theta. Now, the trick is, of course, that he's accelerating up the slope. So he's accelerating up the slope because the center of his circle is uphill from him, right? So since he's accelerating that way, we've got to do axes that way as well. So there we go. So we do tilted axes because he is accelerating towards the center of the circle, and the center of the circle is uphill from him. So breaking this down to components, we have a static friction force. There we go. We have a normal force. Actually, let me just do that slightly more. Yeah, slightly more in the direction of, there we go. And then gravity is going to get broken into components going sort of downslope and then perpendicular to the slope. And since gravity is an angle theta away from our y-axis, this is going to be mg cosine theta, and this is going to be mg, is that right? Yes, mg sine theta. So now we're going to do sum of forces in the, oh, whoops, so I should have done sum of forces here equals ma, okay? Sum of forces in the x direction is static friction force to the right, minus mg sine theta to the left equals his mass times the x component of his acceleration. Sum of forces in the y direction, we've got the normal force going up, we've got mg cosine theta going down, and that's of course going to equal his mass times the y component of his acceleration. Now we look at this acceleration here. So this is the end of the method, of course. We look at his acceleration up here, and the y component of his acceleration, that's the component perpendicular to the flat surface, is 0, because the surface of the merry-go-round is parallel to the plane he's moving in. So he's not accelerating perpendicular to that. And here, he's going around in this circle. We need to find, I think, the maximum omega we can get with this mu s. So obviously, we want to take, well, this is going to be his acceleration here. And what we're going to do, in fact, is we're going to say that's equal to omega squared r. Okay? So, now we can take these equations. We can take the Fy equation. So I'm going to write y up here because I'm taking the Fy equation. And normal force is going to equal mg cosine theta because ay is 0. So I plug that in there, and then that comes over. From the x equations, what we're going to get is the static friction force, okay, minus mg sine theta is going to equal ma. And then we have to plug in that the static friction force is mu times Fn, okay, minus mg. I'm probably taking too many steps here, but what the hell, you only live once. And then Fn is mg cosine theta, so mu mg cosine theta minus mg sine theta equals equals ma. I'm sorry, I have a habit of gripping this stylus tightly, and then my fingers get numb. So then let me just switch to my let's switch to my green canceling pen and cancel out the m's, right? And then we can also gather up the g's here. So what we're going to get is g times mu cosine theta minus sine theta equals a. Okay, and right, so I'm going to switch to a color that's easier to read. We get then a, which is, well, let's go ahead and take our a equals a, right? And then this is what I do for those new to my way of doing things. I set a equal a. 1a comes from a uniform circular motion kinematics, which is this down here. So I'm going to go omega squared r equals, and then the other a comes from your free body diagram and your forces. So a, well, that a is going to be equal to g times mu, and it's mu s, sorry, not just mu s cosine theta minus sine theta. And let me see if I can make that more parentheses looking. Okay. So I guess what you can get then is the maximum omega you can have is omega squared equals g over r times mu s cosine theta minus sine theta. And I think what you have to do, well, no, I know, what you have to do is do the case where, or you have to look, so I did the bottom here, sorry, where friction is going this way, and in fact the normal force is not helping you, and gravity is actually trying to pull you outward. And if you do it at the top, what you'll see, I'll draw a little sketch at the top here, you're going to have the guy, so when you're up here, you're going to have gravity like that, and you're going to have the normal force going like that, okay? And then friction, well, I mean, if you need friction, it will help you go inward like that. But you can see right here that since you're trying to accelerate this way, there's more help, so to speak, for accelerating, for this guy to accelerate down towards the middle, because gravity is working with him. His weight is pulling him downhill toward the inside. So he's all right there. In fact, arguably, you could even look at a case where he's going too slow, where the merry-go-round is going too slow, and rather than him sort of staying up where he wants to be, he's going to slide down inward when he gets up to the top. But we're not going to worry about that. So, but when he's at the top of the merry-go-round, he gets helped by gravity. Okay, so at the bottom, gravity is hurting him. So really, the bottom is the crucial part. The bottom is where he's going to fall off. And so this here gives you the maximum omega he can have. I guess if you want to be really, complete about it, you can take the square root and go square root g over r times mu s cosine theta minus sine theta. And then plug in the values of theta you got. What did I say for theta? Like 30 degrees, 25 degrees, 35 something, and mu s 0.650. I remember the radius was 1 meter, and so then g 9.8, and whatever it comes out to be. But that's the answer.